80 of these things, you know. It's insane. How many of these go? I know. Me and my in collaboration. And like this, I'm going to start changing these things, you know. Got it. Okay, good. Let's see, as soon as my oh, there it goes, it's 3 p.m. So let me welcome everybody once again to the online SPICE SPIN+X seminar series organized here in the Spin Phenomena Interdisciplinary Center SPICE that I run together with Angela Wittmann and Karen Evers-Rosette now in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center led by Martina Schliemann, Luca Hillebrands, and Matthias Chloe in Mainz. Again, this is a webinar format where you see the speakers and the panelists. Please raise your hand or write in the chat to request a question or in the Q&A, and then I will promote you to, after the talk, to give the seminar. Whenever we have, whenever there's a conflicting conference, so we don't have a seminar. So for example, next week we have SPICE workshop, and therefore we will have no seminar. But the week after, so far as we know, we have Jeffrey Beach scheduled, but we still have to get this title. If not, there will be a change, but please check out the schedule that we're still going on through the summer at least. Most possibly in August, we will have a break like everybody does. Today it's a pleasure to have Carlos Rojas-Sanchez, who is now a permanent researcher at CNRS at the Institute in Lamoa. He's actually from South America, from Peru, from Lima, and then studied in Bariloche in Argentina in 2011 and became a postdoc and very successful junior career with the team and work with Al Prefert. He's very well known in spin color electronics, like spin electronics, spin current, and spin Hall effect, and some beautiful work that he did in understanding and elucidated the Edelstein effect in quasi 2D and 3D hybrid systems. And for this work, very nice work, is also gotten recently the CNRS bronze medal, which is also a very high honor in the CNRS of essentially upcoming stars. Now he's actually joining us not today from France, but from New York. But thank him for that. And go ahead, Carlos, start your thing, and then we're looking forward to your talk. And I'll go ahead and mute myself here to give you more band stream, and then we're looking forward to your talk. Thank you.
Okay, hello everyone. Thank you, Jairo, for the nice introduction, and thanks all the Spin Phenomena and SPICE and SPIN+X team for the invitation. And I'm very excited to have this opportunity to tell you our experimental results in ferrimagnetic material. So today I want to tell you about our studying a couple of systems. The first one where we use cobalt terbium ferrimagnet, and we exploit the spin Hall effect of tungsten to manipulate the perpendicular magnetization of cobalt terbium. And in the second part, we will show that some magnetic material having a strong spin orbit coupling can also have a good spin current emitter. And under the right condition, we can either quantify that or exploit to get the cell torque or the spin orbiter switching in single layers. So before continuous, let me tell you, as Jairo said, I am currently a visiting scholar at NYU in the group of Professor Andy Kang, thanks to our Ultimate project. And we're strengthening our collaboration. For instance, we have a joint PhD position. Your students are interested. This is funded by Logan University, or also Andy have a postdoc position at NYU. You are more interested in that, you can look at this website direction. So as Jairo said, I am a CNRS researcher at Institut Jean Lamour, who is in the east of France, like 1 hour and a half from Paris in the fast speed train. So in one day we can do the round trip. You are very welcome to visit us. Here we are in our new building, and we're about 500 people. We have many nice facilities. Let me show you just a couple of them. One of these is our platform for grow thin films. combining many chamber. We have up to 70 meters of ultra-high vacuum, but it's not an empty tube. We have connected several, a number of MVE and PVD chambers, one PED and one LD, and with several in situ characterization, such as a spin resolution RPs. Other facility that we have is the clean room facility, and we have all the basic stuff to do optical and EV lithography. And I am the responsible of this platform, but my main activity is research, and I belong to one of the 23 groups, research group of the Institute Jan Amor, is the SPIN group, and here we are the 15 permanents, and here some of our main research topics. And I am very passionate, as Jairo mentioned, developing this research line, spin orbitronics and spin calorictronics. So in every days, we enjoy with our students and postdoc to playing to manipulate a magnetic element, either with external magnetic field, such as when we were kids, or sense to new phenomena using spin orbit coupling with electrical current of an electrical signal. And this new phenomena is based in that we call sharp to spin current conversion. One of these ways is to sense to spin orbit coupling is happening in BAL or also interfacial materials due to scattering. So here, when we inject a sharp current, we sense to spin orbit coupling, we generate a transversal spin current, for instance, in a nanowire of platinum. And we have also other materials where we can find in the reciprocal space helical spin texture or spin momentum locking, and this is known as Edstein effect or inverse spin galvanic effect, where we inject also a sharp current, we generate a two-dimensional, a spin accumulation, which can diffuse as a spin current in a touch system. This is the sharp to spin conversion, but the reciprocal effect also exists, and somehow we inject a spin current on the system, we generate a transversal sharp current. And for instance, we have done that in the last year using spin pumping voltage at ferromagnetic resonance condition. So here we have a magnetic layer and under a microwave excitation, and we sweep a DC magnetic field. When our magnetic layer, the system reaches the resonant condition, we may process strongly this magnetization, and we generate out of equilibrium spin accumulation at this interface. And we have attached a system with strong spin orbit coupling, then this spin accumulation could relax as a spin current. In turn, this spin current is converted thanks to spin orbit coupling in a sharp current. And we have measured different systems. This is a powerful method to evaluate the efficiency of spin sharp current conversion. For instance, we have studied many heavy metals of Rashba interface, topological insulator, at room temperature of this oxide Rashba interface at low temperature. And we have evaluated that and compared recently in this paper, and we found a relative advantage of topological insulator at room temperature of Rashba oxide at low temperature. And this is a large advantage. We anticipate, for example, large advantage for the reciprocal effect, such as in spin calorictronics. This advantage, however, is reduced in the direct effect, depending also of the property of the layer, like the magnetic or the interface, if we have metallic channels. But today I want to focus in the direct effect, sharp to spin conversion, and some of these application. So once again, when we inject a sharp current, we generate a transversal spin current. The efficiency of this conversion is called the spin Hall angle. We can look at some nice review here, for instance. And thanks to this seminal work in 2011 and in 2012, we know that instead of sweeping a perpendicular magnetic field to manipulate this perpendicular magnetization, now if we sweep the in-plane current, we can get this similar manipulation, and that we know as a spin orbital switching of current-induced magnetization switching. This leads to the development of a three-terminal spin orbital MRAM, and this switching is really fast, below the nanoseconds, in a project led by John Gorshon, also in the Institute Jan Amor in Nancy. We have showed this switching with only a few picoseconds. So with that, let me continue my talk with the following outline. So in the first part, I want to tell you about our study in tungsten cobalt terbium, when we, as I said, we explore the spin Hall effect on tungsten, and we find out that this is a very robust system to get this spin orbital, and with the huge advantage of the heating effect, a system of the heating effect. And in the second part, I will show you that this gadolinium iron cobalt have a strong spin orbit coupling too, and is a good emitter of the spin current and efficiency torque on the magnetization dynamic of permalloy magnetic layer. And in the last part, I will show you the conditions to exploit this spin current emission from the magnetic layer to generate that we could call a cell torque. So let me briefly recall some properties of rare earth transition metal ferrimagnetic alloys. So we have on those systems two magnetic sublattice. One is given by the rare earth and the other by the transition metal with different temperature dependence. So as a consequence, we will have different characteristic temperature in the net magnetization. The first one we can find here is one, both sublattice are compensated, so the net magnetization heat is 0. And because the gyromagnetic ratio of the give the relationship with the angular moment and the magnetization is different for rare earth and transition metal, then we have also a different characteristic temperature called angular compensation temperature. So at this point here, on this temperature, that we find out is the angular compensation temperature is 0. Typically is higher than Tm. So that is two characteristic temperature. The other one is, of course, the Curie temperature when the system is no longer ferrimagnet, but typically paramagnetic. There is other characteristic temperature, I think, reported recently by this theoretical work, where they have this condition, dmdt equals 0, to they say that in also amorphous ferrimagnetic material, there is a self-production of a spin current driven by magnons. That is canceled out at this point. Just to remember, so below the M, the net magnetization and the angular magnetic moment are antiparallel, as about a similar case about angular compensation. However, between Tm and Ta, this magnetization, net magnetization and net angular moment are parallel, and that will lead up for some characteristics for the cell torque that will be different, that we could call now the external spin orbit torque. So now in our case, we have this system, 3 nanometer of tungsten and then 3.5 nanometer of cobalt terbium, capping with aluminum that is naturally passivate. So the advantage of this cobalt terbium that even that is amorphous, have a Ball spin orbit coupling with magnetization out of the plane. So it's relatively easy to integrate with any other system. In our study, we changed the composition between 72 up to 86 of cobalt, and in the 72 case, the magnetization is dominated by the terbium, and 86 is dominated by cobalt, and at some point between two, we'll have a net a compensation of these two magnetization. That is the magnetic compensation point. And we can evaluate this as function of compensation of temperature. One method is to use magnetotransport. So we could pattern our sample in a whole bar, and here we inject a current in a channel, and we measure the voltage in the transversal channel while sweeping our perpendicular field. We use little current, only 400 microns. So that we can see here is the following. At 300 Kelvin, we can see here a full typical cycle, the whole resistance versus the perpendicular field. When we increase temperature, we increase the coercitive. At this temperature, 320 Kelvin, we don't have enough field to reach the coercitive. And above this temperature, we see again a cycle. But one characteristic is that the switching polarity change. So we call this as a, let's say, positive at 310 Kelvin. At 325 and 350 Kelvin is negative. So that is one signature that tells us that we overcome the magnetization compensation temperature. And one way, this is so straightforward to allow us to estimate the magnetization compensation temperature experimentally. There is different ways to estimate the angular compensation temperature, measuring, for example, the magnetic damping constant, or more recently by domain wall propagation in this nice work by King, Professor Lee, and Teruono collaboration. Well, other ways to estimate this is a room temperature. For example, we have a study in the squid magnetometry, a different concentration of cobalt. So here in the left, what we observe is the coercitive, and in the right, is the next saturation magnetization. That we can see that the coercitive tends to diverge at this value of cobalt, while the net saturation magnetization tends to 0. This is typical feature of when we reach the magnetic compensation point. Here again, in using magnetotransport in another whole bar, we can see the evolution of the coercitive that decrease when we increase temperature, and when we start to reach the magnetic compensation temperature seems to diverge. And the switching polarity with the perpendicular magnetic field is this: one sign below Tm and the opposite sign above Tm. So this is all the feature in ferromagnet system. But I say nothing new for people working in ferromagnet system, as my colleagues in ANSI. So this is well known by 30, 40 years. But now we can exploit these materials combining with the heavy metal with a strong spin orbit coupling. And here that we do is in the left, the typical experiment, the way we manipulate magnetization with perpendicular field, and in sample with terbium rich, and the bottom cobalt rich at room temperature. And here in the middle, in the right panel, that we do is the spin orbital experiment. So instead of sweeping perpendicular field, here we're sweeping in-plane current. And we can see that we reproduce a nice cycle. So we have a sharp switching, we have the same amplitude as here, and we need still a small in-plane field. When we change this small in-plane field, we change the sign of the polarity. So all these features agree what we know with the spin orbital. In this case, we can is due to the spin Hall effect in tungsten. So well, everything looks well. We are happy. However, there is something that is unexpected. If we look here in this sample with the terbium rich, the switching polarity is the same than here, and it's expected the opposite. And we have different questions why we have this behavior. And one explanation is because we are using now much more current, up to 20 milliamp or 24 in some samples. So we're hitting strongly this system. Tungsten and cobalt terbium are both layer resistive, about 150 and 180 micron centimeter. So in order to check this unexpected behavior in this terbium-rich sample, we did the following experiment. We measure again the classical experiment, Hall resistance, while sweeping perpendicular field, but now instead of using little current, we change the amplitude of this, the intensity of this current, pulse current, between 5 milliamps up to 34 milliamps. And we can see here that between 19 and 20 milliamps, the polarity of the cycle change. As I addressed or highlighted, this is a feature that we overcome the magnetic compensation temperature. And in these particular devices, the critical current here to switch the perpendicular magnetization is 24 milliamps. So it means that the device at room temperature is terbium rich, but because we are using large current, in our experiment, we hit at about the magnetic compensation temperature. So we can withdraw the following conclusion, that the switching, the sample temperature at which we obtain the spin orbital switching is above the magnetic compensation temperature, also angular, we have calculated that, and above the initial temperature of our device, and below the Curie temperature, because we can see that even a much higher current, the sample is still magnetic with magnetization out of the plane. So we resolved the first mystery, and then we further studied the whole series at different temperature. So here, for example, in another sample, in another concentration of cobalt, in the top panel, we show again the spin orbital switching experiment. So this is the transversal resistance as function of current. We observe a nice cycle and sharp switching. And in the bottom, in addition, now we're measuring also the longitudinal resistance. So the resistance of where the channel we apply the current. And this is equivalent to measure, a value of resistance is equivalent to have an information of temperature of our current channel. That is interesting is that if we follow here a different initial temperature, this vertical dashed line will reach at the same level of resistance. So the same level of resistance means that we are reaching the same temperature in our devices. Further, we can estimate this experimentally, this temperature, just performing resistance versus temperature, now with little current, and in this particular concentration, we have about 485 Kelvin. And we have called this switching temperature. And we have studied all the series, and it depends on in this case, and it depends on the composition. And we believe that this is a kind of new characteristic temperature in this resistive system, tungsten cobalt terbium. So that is I wanted to tell you in this case of tungsten cobalt terbium. Before the summary of this first part, let me acknowledge all our collaborators in SPIN-Tech, in Grenoble, our team in Nancy, and particularly I'm grateful to Taya Pan, my former PhD student. So the summary of my first part is here. We have studied different composition in this tungsten cobalt terbium ferromagnetic based system. We have obtained a nice spin orbital switching at different composition and temperature. And we have we're reporting a new characteristic temperature, the switching temperature, which scale with the Curie temperature, because this switching temperature increase with composition of cobalt, while angular and magnetic composition temperature decrease when we increase cobalt concentration. The switching current is in the order of any other heavy metal ferromagnetic system reported, or 10 to 11 ampere over square meter. That is important is that we need only, little in plane field to get the full switching. Down to 2 millitesla, we already obtained the 100% switching of the magnetization. So why is that? That we believe is that actually because both layers are high resistive, we are hitting a lot, but this is indeed is an advantage because when we hit, this allows us to strongly reduce the perpendicular anisotropy. So that is why we need only little in plane field to get this switching. That's not the case. We have not reported that, but we have measured when we have, for example, a bilayer of platinum cobalt terbium. So here, most of the current flow in platinum, and we don't have the same heating effect. So it's hard, a bit more difficult to get the switching here. We got it, but we need higher in plane field. So this is that I wanted to report in the first part of my talk using the external, spin Hall effect, external spin orbital, using the spin Hall effect on tungsten to manipulate this magnetization in cobalt terbium. So now let me move to the second part of my talk, where we study gadolinium iron cobalt. So as I say, for a while, we look material with a strong spin orbital coupling, and we have overlooked that some magnetic materials can also be a good spin current emitter, and that is that we have studied here. So let's remember that in addition of a magnetic material could emit a spin current with this spin polarization parallel to its magnetization, but also can have this symmetry that we equivalent to a heavy metal, where this spin polarization is perpendicular to the charge current we inject. And this we could call the spin Hall effect light symmetry, and this after this work of Taniguchi, Grolier, and Style, spin anomaly Hall effect symmetry. There is more theoretical work in the recent years, and one of the last one is, for example, by Professor Lee in 2020, where they explain why it survived this spin Hall effect symmetry. But let's resume this part as the following. So we have this, we focus on these two different symmetry of the spin current emitted by a magnetic material. The spin Hall effect light, where this spin polarization is perpendicular to the magnetization, and the spin anomaly Hall effect light, where this spin polarization is parallel to its magnetization. The spin anomaly Hall effect light and spin Hall effect light have been measured experimentally in different material. For example, in this work of Vera Maroon, they compare permalloy on a mesa of jig permalloy again to study no local signal and compare it with platinum. And they reported that the overall efficiency in permalloy is equivalent to the one of platinum. Another work is in cobalt iron boron by Satoshi Hiyama and co-workers in Japan. So they reported up to 0.14 spin anomaly Hall effect efficiency in cobalt iron boron using spin-torque ferromagnetic resonance and modulation of damping. Indeed, this is the technique that we will use also to study our gadolinium iron cobalt. So we have this picture here of our device. We inject a radio frequency or microwave current, and in addition, we can add a DC bias current to analyze the damping modulation. So here our main system, we have a 3-layer 10 nanometer of gadolinium iron cobalt, 4 or 6 nanometer of copper, and 4 nanometer of permalloy. When we sweep the DC field, we get the resonant condition. Here in the left is the resonant condition of permalloy. So this means that we process the magnetization of permalloy. And in the right, we process the magnetization of gadolinium iron cobalt. We can use this as any ferromagnetic resonance experiment. So we can perform, for example, frequency dependence to study anisotropy or to study the magnetic damping constant of each layer. But we want to quantify the charge-to-spin current conversion in those systems. So for that, we will focus on this permanent resonance, because here, when we inject the current flowing in gadolinium cobalt generate a spin current that may exert a torque on the magnetization dynamic of permalloy. And how can we evaluate that? For that, let's remember that in this experiment, the DC longitudinal voltage that we measure is proportional to the AMR of the magnetic material. In this case, permalloy have an advantage, and also to the amplitude of the radio frequency current, and the spin orbital driving fields here is in spheric coordinates, and to the components of the susceptibility matrix of permalloy. So we could do all the analysis of this, and we find out that those are only proportional to the contribution of the spin Hall effect symmetry. So it means that here we cannot use to study the spin anomaly Hall effect symmetry that we are interested to know. And in order to get that, if we now added, in addition to the radio frequency current, a DC current, then we change this magnetic susceptibility component, and those are depend of the direction along the equilibrium position of permalloy. In that case, we get that changing the line width of permalloy is proportional to both the spin Hall effect symmetry and the spin anomaly Hall effect symmetry. So using then this experiment, radio frequency field plus a DC bias current, we can access to this efficiency that we are interested to know. Let's first study a control sample, for example, cover permalloy. Here our bilayer. In the top, we have all the spectrum at different frequency, and in the bottom, the line width versus the DC bias current. And we can see that there is no modulation of damping at this frequency in this bilayer. This is as expected because, of course, copper have a good spin overcoupling, is a good spin overcoupling material. So then let's see our main results in the 3-layer. So here in the left, we have the result of gadolinium cobalt copper permalloy. We can see that there is a nice variation of the line width versus the DC current. We could quantify this, and it's really a large value, overall efficiency of 0.8. We redo other samples and changing, for example, the thickness of copper, and again, it's really large value. And we wait for control samples to make sure that those results are reliable. And in this very well-known spin Hall effect material, using platinum now, we can see again a nice variation of line width. And when we quantify this, we get above 0.03. So all this is consistent with other reports in platinum. So we now are, that's made reliable our result also in gadolinium iron cobalt. And we can say that overall efficiency in gadolinium iron cobalt interface with copper is about 25 times more efficiency than in the system platinum copper to exert a torque on the magnetization dynamic of permalloy. So that is nice results. We are, convinced of the result. We have this large or huge overall efficiency in gadolinium iron cobalt, but there is still some open question. For example, we know that gadolinium iron cobalt is a material with Ball spin-orbit coupling, and it has been reported that gadolinium and gadolinium oxide is a magnetic rush by interface. So we can know so far with those experiments, this entangle is more of the contribution is coming from Ball or from interface. So now I move to the last part of my talk, where we first quantify the spin orbital in single gadolinium iron cobalt, and then we can play with the characteristic temperature to observe to make the difference with the external spin orbital. So as I mentioned, we have in a magnetic material a spin current emitting with these two symmetry. One, when the spin polarization is parallel to magnetization, of course, there is no way to generate cell torque. However, in this symmetry, the spin Hall effect lies because spin polarization is perpendicular to magnetization. Under the right condition, we can get the spin orbital of cell torque. And what are these conditions is that this spin current emitting from the magnetic layer should be absorbed outside. For that, we need a good spin layer. And a good spin layer could be another, a heavy metal, a material with a strong spin-orbit coupling, a magnetic material, or a resistive material with a thickness above its spin diffusion length. We're working to optimize this on different systems. Indeed, it has been reported spin orbital switching in single magnetic layer in different systems, such as iron platinum or cobalt terbium, or gadolinium iron cobalt interface with aluminum or permalloy. This is not exhaustive, just only some example in the recent years. But the path that we will follow is to fulfill the condition of having a good spin sink attached to our system. So for that, to quantify the spin orbital in single magnetic layer, one of the tools that we have is the second harmonic. So this is a very powerful, simple and relative, yes, it's relative simple and powerful tool to quantify the spin orbital. So now we pattern our samples in a whole bar, and again we measure the transversal, we inject AC current in one channel, and we measure the transversal current in the other channel, and we have the different geometries of measurement. When the in-plane field is parallel to the inject current, that allow us to estimate the damping light spin orbital efficiency, and when the in-plane field is perpendicular to the inject current, and then allow us to estimate the field light spin orbital efficiency or effective field. And in the first harmonic, when we have this system with magnetization perpendicular to the plane, the first harmonic around the equilibrium position is a parabolic behavior, and the second harmonic around zero field is a linear behavior. We can quantify this following this single expression, which is the slope of the second harmonic over the coefficient of the parabolic behavior of the first harmonic. In the limit of around zero field, and when the planar Hall effect is much smaller than the anomalous Hall effect. Some signature of this is the following. In the damping light configuration, we can see here that the slope is the same for both states, either if the magnetization is up or down in our system. However, in the field light configuration, it changed with the initial state of our system. And I will use this to discuss about the signature of the cell torque. So we can see here that the slope is very small, it's weak, and that is not surprising because our system here is gadolinium iron cobalt with copper, and copper alone is not a good spin sink. However, if we add a good spin sink to our system, we should enhance this harmonic signal. And here, a summary of our results in three systems. A bilayer gadolinium, iron, cobalt, copper. Then we add tantalum on top of this bilayer in this star symbol here, or we add platinum in another sample. We can see that with copper there is a weak signal as expected because it's not a good spin sink layer. When we have tantalum, the signal is weak but positive, change the sign. And when we have platinum, the signal increase, it's a large signal but positive too. And we can explain that in the following way. So in the case of platinum, we have an addition of the cell torque plus the spin Hall effect of platinum. Now that we have a good spin sink layer also with tantalum, we have a subtraction of the cell torque and the spin Hall effect coming from tantalum. Further, we can quantify what is the contribution of the cell torque. And we can combine these, do a slope, or for example, we can analyze the damping light in these three layers, gadolinium, iron, cobalt, copper, platinum. So the relation is given simply by this equation here. So we have the total damping light measured in these three layers by these square or diamond blue points. And that we say is that we have the cell torque plus the contribution of the spin Hall effect coming from platinum. We know this. In order to know this, we can renormalize because independently we have measured the spin Hall angle of platinum. So using this expression, we can calculate the contribution of the spin Hall effect of platinum in our three layers. So now we know all these terms, and then we can calculate the cell torque contribution. The contribution of the cell torque in this gadolinium, iron, cobalt interface with copper. And we can see that is of the same order of platinum. It's quite close. So it's a large effect. And let's remember that in this case, in the cell torque, it's only the spin Hall effect light symmetry. And that is that we wanted to show you. So we have optimized adding either platinum or tantalum to quantify the cell torque in this gadolinium, iron, cobalt, copper. And that's have performed at room temperature. Now I want to tell you how we could make a difference of that we call the external cell torque and the cell torque. So here is a bilayer, another bilayer with copper. And we can see that when the sample is gadolinium dominant, we have this positive slope in the second harmonic of the damping light experiment, second harmonic experiment. And when the sample is 340 Kelvin with this iron cobalt dominant, we have the same slope. And if we normalize by the initial state, it means that the damping light effective field driving the spin orbital change in sign. It's given by this simple expression. And in this study, we have anticipated, now I'm playing with the characteristic temperature, we have anticipated that both the damping light and field light effective field change in signs at magnetic compensation temperature, and again have angular compensation temperature. Made the long story short, and that is related because between these two temperatures, both the net angular moment and net magnetic moment are parallel between these two temperatures. So that is that we have anticipated, and we have shown in the case of TM. And the open question still is if the spin orbital switching polarity keep the same sign, or will according to this change sign of damping light torque, or we will observe a different polarity. I will show some example later. With that, we can see if we look in any study, in any report, in bilayer of ferrimagnet with a heavy metal, this behavior is different. So that I'm saying is that when the sample is rare earth dominant and when the sample is transition metal dominant, the slope of the damping light are different. We can look, for example, on these reports. in platinum cobalt gadolinium, tantalum gadolinium iron cobalt, or tantalum gadolinium, sorry, again, this tantalum gadolinium iron cobalt. And of course, we can say that could be because the way we measure or some artifacts. So we, using the same protocol, we have our own data, and Eloise measured here in the bottom this gadolinium iron cobalt platinum. And here the system is dominated by what we call the external spin orbiter, I mean the spin Hall effect of platinum. And we can see that when the sample is gadolinium dominant at low temperature, we have one slope for the second harmonic, and when the sample is iron cobalt dominant, we have the opposite slope. So this behavior is totally different than this. And that is one signature that we can exploit to make sure that we are our system is dominated by either the cell Tor, the cell spin orbiter, or by the external spin orbiter from an experimental point of view. And here more data that Eloise had measured recently in this bilayer gadolinium iron cobalt copper, and we can see here that a function of temperature, the damping light effective field change signs are around a magnetic compensation point. And in order to compare here our own data with platinum, we can see that here we keep the same sign. Here the values are much higher than here, of course, because this system is not yet optimized. So here we don't have a good spin sync layer, but that we want to highlight is the chain of this damping light effective field here. That chain is signed. We can look in the case of that we call the external spin orbiter, I mean heavy metal and ferrimagnet bilayer in for example on some of these papers or on these reviews in ferrimagnetic spintronics. So the other and actually there is one recent study that they observe this double chain of signs using thick iron terbium, but not as function of temperature, but of composition, which is equivalent. So they observe a chain of the damping light effective field at magnetic compensation point, and then again at angular compensation point. So now the other characteristic that we could exploit, but this is still an open question, is the polarity of the spin orbiter switching. So here, for example, from this reference, we observe that is because the anomalous Hall effect, which is a shard-to-shard phenomenon independent of the electron coming from the transition metal. So what we observe here is a chain of the polarity in the spin orbiter experiment. So this is a sweeping of in-plane current, and we can see that when the system is here in blue is a cobalt iron rich, we have a given polarity, but in the red curve, when the system is gadolinium rich, we have the opposite polarity. So that is that we have measured in different heavy metal ferrimagnet bilayers. And so the open question is, experimentally, is what will be the switching polarity when we have the cell Tor. And we believe that we keep the same switching polarity. And those are recent data performed by Eloise. So, but we're optimizing this spin sync. It's still a work in progress. And we believe that in the case of the cell Tor, according to the result of the damping light effective field, we should observe the same polarity when we have that we call cell Tor. So with that, that's it that I want to show you today in the case of gadolinium iron cobalt study and in the exploiting the characteristic temperature in a ferrimagnetic material. So before then on my talk, let me show quickly an advertisement. We're organizing a workshop in Argentina, in Patagonia. It's really a nice place, Patagonia, Argentina, in November, and there is still a couple of weeks left to submit abstract, and there is a slot for contribute talk and poster. And before my conclusion, let me acknowledge all this a long collaboration, all of our collaborators, Christoph in Singapore, Professor Shufen Chang and his student in Arizona, and Albert Vansan and David in Senegal, our team in Nancy, particularly Sebastian with Petit Quadlo and Michelin, and of course our student who performed most of the experimental work, David and Eloise Damas. With that, I come to the end of my talk. So in the summary of my second part, we wanted to show you that magnetic materials could also they could be also good spin current emitter. We have studied the case of gallium iron cobalt interface with copper, and we show overall efficiency spin anomalous Hall effect plus spin Hall effect symmetry much larger than in the case of platinum. We could disentangle this contribution combining, for example, a spin torque ferromagnetic resonance with the DC bias current and second harmonic experiments. And if we optimize the system with a good spin layer, then we can have the right condition to exploit or to achieve the cell torque of equivalent the switching in a single ferrimagnetic layer. Of course, there is, still open question, but also perspective. We are optimizing the spin layer to get the switching without any external heavy metal or magnetic layer, and those systems are also good for dim eye production, Scarmion motion, and so on. And those work are related in these two recent publications. With that, I finish my presentation, and I will be glad to discuss with you and to answer your questions. Thank you very much.
Thank you. So we'll begin maybe the questions. Please raise your hands if you have some questions, and I will promote you to panelist. Within the panelists, you just kind of mute yourself and ask your question if you like. I'll go ahead and start a little bit. So in this spin anomalous Hall effect, is this, you had, of course, this combination of the different layers to disentangle, but is then still primarily a surface effect, or essentially where you are inducing the torque in the ferromagnetic itself?
This is still an open question for us. We have the Ball spin orbit coupling in ferrimagnets. So gallium iron cobalt itself should be a good spin current emitter, right? Mm-hmm. But also we are preliminary result changing the copper interface, for example, titanium of aluminum. And it seems that the torque change, there is a large variation, or even maybe the design, but we're checking that. So from the experimental part, we have to study other interface here. And that is a work in progress in collaboration with a group in Poland, for example, and also in NYU. So far, it's an open question, is the main contribution come from the bulk or from the interface?
Because from the point of view of the bulk, an angle of spin Hall angle of or an effective spin Hall angle of 0.49, it's difficult to consider it as part of a transport-induced current, because the angle itself is enormous. You would have to probably go to second order or something like that. On the other hand, if it's part of a contribution from accumulation at the interface or from the broken inversion symmetries there, one can envision that, okay, if that geometry of that symmetry works out, but then you have a strong contribution, then it can work out. I guess I'm always suspicious of these very, very large numbers, like, whenever you had these very large, let me promote Piro here, these very large numbers at the beginning when they were studying spin Hall angle of 3. Yeah, it's like, makes no sense. Yeah, no, it had to be, it was essentially a spin orbit torque, of course, and using spin orbit coupling at the ferromagnetic itself. Still, at the end of the day, efficiency is efficiency. That's what you worry about or care about. But to maximize it is difficult. So go ahead, Philip. Go ahead and ask a question, and I'll follow up later on with more questions for myself.
Hi, Carlos. Very nice talk.
Hi,
maybe let me formulate it a little bit provocative, but if the effective spin Hall angle or the effective anomalous Hall and spin Hall angle is so large, what is the drawback of this mechanism in general? Why should we use platinum at all for our devices if you can do it much better with gadolinium iron cobalt?
I mean, we have a strong spin Orbital coupling gadolinium cobalt because it's bringing by the 5D band of gadolinium. But the torque, if we where is it? We have large value, but actually here we compare the torque. That matter is
and that
the cell torque is large, but is still slightly smaller than the case of platinum. So I don't know if that's
yeah, principally so, but in the end, if you then do the, let's say the comparison to the damping, if you have in a SYN system in addition with platinum, usually you could have a lower threshold for an auto oscillation, yes? Because the threshold of the auto oscillation would be something like the torque over the damping, yes?
I don't get it about the oscillation, sorry.
So if you drive an auto oscillation using any spin injection, you always have, you have the parameter that you need to inject the torque or you inject the spin, and you have to fight against the damping in the material.
Yeah, that is a okay. So here, this is only the spin Hall effect light contribution for the cell torque. That is, I mean, it's large, but still slightly smaller than platinum. Now, if we somehow could exploit both a spin anomalous Hall effect and a spin Hall effect, that is larger, and that is the way experimental measure here. I mean, this variation here is proportional to the torque exerted from the bottom layer on the magnetization dynamic of permalloy. And that's, I mean, is that we observe, despite that gadolinium cobalt is more resistive than platinum, we observe, a huge, a large value, 25.
Yeah. Okay, so then I just wanted to make sure that I understand that correctly. So this is really this 25 times more efficient effect on the dynamics.
That we did here is we quantify this chart to spin conversion. We have both symmetry in gadolinium iron cobalt, and is 25 times larger than the spin Hall effect efficiency in platinum. And in this experiment that we did is we add the DC current, and we either enhance or reduce the line width of the permanent resonance. And then we could quantify, following this slope here, this efficiency. I don't know if that's...
exactly. I just wanted to make sure that I got this right, that this is really...
Yeah, it would be the one that you would obtain, that you would inject, essentially, in the oscillation. At the end of the day, that's what it is measuring. So I was trying to figure out the origin of it, but the efficiency is there. Giovanni, I'll go ahead next, and then Don Cook afterwards.
All right, thank you, Carlos. So I have one question. So are you aware if there is some electromigration problem in these materials? Because as you know, in platinum, when the current increases, you have some electromigration. So this give you, for example, when you want to read out to the resistance, this give you some problems. So my question is, are you aware if you can have electromigration here, or if it is happen at which current, so this can be more about resistance switching.
We have performed some structural characterization, and the variation, there is a little maybe interfusion with the substrate, but the composition variation in the vertical direction is weak, is very small. And the current that we add here, the current density is not so high in this experiment. So this experiment is not for a switching experiment. It's just, we can quantify 5 milliamps. I guess it's the order of 10 to 7 ampere over square meter. So it's not so high in this experiment, the current density.
May I ask you another question?
Yes, of course.
So the other question is about the efficiency when you increase the thickness of the material. So for example, if you have a platinum, when you increase the thickness of the ferromagnet to antiferromagnet couplet, actually the torque scale with thickness. So do you have for this self-torque is still there when you increase the thickness of the material in order to, let's say, have a larger, let's say, a larger device in the sense, a thicker device? So is this depends on thickness or not?
We haven't performed a signal dependence, but like with platinum, we believe that I think it will depend of signals, the overall efficiency. When we have the magnetic layer with a good spin sink, but other than heavy metal and magnetic, because if we have heavy metal and magnetic, then it's much more complicated to evaluate the cell torque. But it should depend also of signals like the external spin orbit torque.
All right, thank you.
Okay, Dong-Wook.
First of all, thank you very much for a very interesting talk. I have one question and another question/comment. So the first question is probably because I really don't know this material very well. So in my understanding, your experimental method relies on the resistance measurement. So you electrically measure the direction of magnetization of gadolinium iron cobalt sample by measuring some like hole resistance or other resistance. And my question here is that you change the temperature or composition of the compound, and the sample goes through a transition temperature for like a magnetic moment compensation or angular momentum compensation temperatures. And I suspect that whether this is going to change some dependence on the planar Hall effect or anomalous Hall effect, and I suspect that it might actually affect characterization of the experiments. So could you answer to this question, please?
That's right. I mean, when we add here current, depending on the intensity of current, we hit the sample, and depending on the intensity of current, we may hit too much that we overcome the magnetic compensation temperature. That is that we observe in the switching experiment in tungsten cobalt terbium, for instance. But here in second harmonic, we apply low current. So the current density is not large enough to overcome the magnetic compensation temperature. And here, here is an example of that. I don't remember the value of current, but it's a few milliamps. The current density is smaller than, we made sure to not overcome the magnetic compensation temperature in this experiment, not intentionally. So we set the temperature in the cryostat, and here the current density that we use is a little, let's say, little current compared with the switching experiment.
Yeah, actually, one concern that I had for quite some time is that, this method was originally developed for a very simple ferromagnetic system like iron or cobalt iron or permalloy, and it seems like we still apply the same technique for more complicated ferromagnets or other magnetic compounds. And I always wondered whether there is a point where we really have to be careful about applying the same method for, intrinsically more complicated ferromagnets, because here in gadolinium iron cobalt, there are two magnetic moments, one from gadolinium itself, but also the others from iron or cobalt. So yeah, I'm just
but I think the dynamics of the energy equation will still govern. You just have to have some rescaling. So from the point of view of the measuring of the torque, I don't see how this homogeneous dynamics that they measured would be any different.
Yeah, but what I was worried is that actually some property might change across the transition temperatures. But Carlos answered that.
That changed, but as I say, it has been developed. Consider LG equation for each magnetic sublattice, and we could find similar relationship for the experimental characterization of this torque. And that, as you say, the characteristic temperature is important here. and that's it that we can exploit to, I believe, to make the difference of the cell torque and the external spin orbital. For example, if we have a ferromagnetic layer, we cannot find out this, I don't know, for example, cobalt platinum. Of course, then it's external spin orbital. But if we have another ferromagnetic layer with a strong spin orbital coupling, and we believe that we may have cell torque, at least we cannot use this. I mean, we don't have characteristic temperature to show experimentally this difference.
I see. Another question or comments that I have is that on the perspective that you have shown at the very end, that the self-torque can possibly open the way to design spin-orbit torque system as spin-orbit torque devices with light elements without using heavy elements. And then another direction that I'm actually currently thinking is probably using orbital current. And I also think that maybe orbital current might be relevant in this system too, because at least in my previous calculations, it seems like self-induced torque and orbital torque seem to, satisfy similar conditions. But I mean, it's not very clear to me either. But I'm just wondering how you think about this.
Oh, that will be.
Have you considered orbital current in your experiments? Great. Because it also has gadolinium, so there could be some sort of orbital to spin conversion in gadolinium by spin orbit.
But remember, he's always measuring the torque. So whatever the contribution is with the spin or the orbital, he's just measuring that torque. And he's measuring in terms of flux of angular momentum. That's what he measures.
Oh, at the end, yes.
Torque the other day, it's just about us having to give them a way to distinguish them by like he's doing this. Sorry, Carlos, I'm gonna comment on that, because then it's about really trying to distinguish between the layers or some other mechanisms that we can hand them to distinguish them. But right now, the measurement itself, these measurements are really measuring torque.
You're right. I fully agree.
It's in an influx of angular momentum, wherever they come from, whether it's from the spin sector or the orbital sector dominant. That's something that they cannot really tell. Of course, if we do a prediction that, okay, that's only a spin sector can give you so much, and then the rest has to be explained by something else, orbital sector can be, of course, one of the pieces. What is ideal is when the orbital sector and the spin sector have a slightly different symmetries, which is, I think, where it will come most important.
Yeah, I completely agree with you.
So experimentally, I think, I mean, well, I just saw a couple of weeks ago, I guess, the nice result that you have with Antonio Acevedo using jig platinum and copper oxide. So,
yes.
To disentangle. So one way could be here, use very thin platinum, and of course aluminum oxide have no independence of this oxide capping here. With copper, probably we can disentangle this, but I mean, that could be another project, another collaboration, and it's always matter of time and hands. So
actually, I was thinking that in this sample is gadolinium, iron, cobalt, and copper aluminum oxide. I was wondering whether orbital current can be generated from aluminum oxide interface. We have seen it actually.
Actually, we believe that with aluminum oxide, no, we don't have. It was hard. Eloise changed this capping layer over here, and for example, gold, it was really hard to challenging for lithography, and she observed again the same change of the damping light. But I think one experiment could be as Antonio Acevedo do with yttrium, iron, garnet, and platinum, changing the thickness of copper oxide here, for example. But I mean, we can discuss that. But it's I mean, very interesting experiment to perform, nice idea, but it's matter of also times and hands.
Yes, if you one day, if you are interested in doing in this direction, we're very happy to discuss.
I will.
Yeah,
I can fully recommend. Tom Hood is one of the pioneers of this orbital contributions on orbitronics, which I think is
thank you.
Want to start with. This is Sayed Hussein. Can you go ahead and? Sorry. Yeah.
Thank you, Carlos. Thank you very much for this very nice presentation and it's a good work, really. So I have a question about, so did you try to measure the anisotropic, is there any anisotropy in your talk? Because it is from the gadolinium iron cobalt. So I don't know if it has some anisotropy in the talk, or, okay. Yeah.
No, we don't think we have some anisotropy here because gadolinium iron cobalt is amorphous. So, I mean, you mean by anisotropy, we measure along one direction or other in the plane,
Yes.
right? Yeah, no, but in this case, no, it's not an epitaxial system, so it's amorphous. We don't see.
Okay, and this torque is sufficient for magnetization switching. Have you tried switching in this system?
We observe switching here, but because we have platinum, and here no, I mean we tried, but we didn't observe switching. I mean, you see at this value are very small. We quantify by current density is small, and here no, but it's not surprising. The system is not optimized with a good spin layer still. When we optimize that, and that's what we're working on, and we observe the switching. But
yeah, because yeah, there's the new paper from Pedram group, is the Nature, I guess it is 1 year old. So it's they show this cobalt terbium gradient, the switching in ferrimagnet. I think this is the only paper that they show ferrimagnet, the switching in single layer ferrimagnet, single system. There is no, yeah, I guess this cobalt terbium. Yeah, this is the one.
Right.
Yeah.
Right. They have observed that.
It's a nice one. Yeah. So. Yeah, that's in the way that the ferrimagnet that work for the switching. Yeah. So have you have not tried yet the switching current switching measurement? Yeah.
We are trying different systems. In some of them, we observe switching. In some of them, not as expected. So the goal is, the path that we follow is to optimize this spin layer, and to measure all these feature of the cell torque. We want a spin layer which is not heavy metal or neither magnetic layer. But this,
okay. Okay, thank you very much.
So let's have the last question from Igor. Igor Sandalov, can you go ahead and ask your question?
Thank you. I just wanted to add to your discussion about orbital moment separation from magnetic moment. So for the case of rare earths with non-zero orbital moment, they are always very sensitive to distortion of the lattice. And probably this is a kind of way to separate or to estimate contribution from this.
Correct.
And another thing I wanted to say, that actually one should have in mind that when
Actually, Igor, can I maybe add to that a little bit what you said? Because I know they are sensitive to that, but in the equilibrium components, one thing that has been surprising with the orbital contributions of the angle, that in the linear response, because they are not the spin-orbit couplet related, that the contributions tend to be stronger as long as we discovered, or as strong as the spin component. And I'm not sure if that may be a thing to explore, to see if strain will change, of course, strongly the orbitals and the contributions, but it's not so clear to me that it would be, but something to explore. I think that's a great tool to look at.
Yeah. Okay, and another thing I wanted to mention is that actually all information through non-magnetic layers goes through electrons via a kind of RKKY interaction. I mean that there are two things are important. First, it's oscillating, and second, it's a drop as 1 over R cube, which means that one has to expect that any effect of this will be smaller if the layer of copper, for example, is thicker. That's what I wanted to say.
Right. That's because we intentionally use thick copper on those experiments and the first part to reduce or to consider that those magnetic layers are not coupled. So these 4 nanometers, 6 nanometers, I think were well above the change between these two layers.
Okay,
thank you. So with this, I think I would like to thank, well, now that some of them have left, but the 150 of you that were here, between YouTube and the talk. And thank Carlos once again for a wonderful talk, as always. And we're looking all forward to this wonderful workshop in Patagonia. My wife. And well, send me the abstract. I promise. And everybody remember, next week we don't have a talk. We will have a SPICE workshop ongoing. And the week after that, we hope to have Jesper Beach. If you know him, and please remind him to send the title and the abstract. Sometimes we don't really know. He doesn't tend to answer emails most of the time, but if not, we'll arrange something else. Okay. So thank you very much all, and have a great, wonderful day. Thank you, Karen, to be on the standby for me, and have a great rest of the day. Thank you.